strength of an acid. In all these reactions, how do we find which reaction is actually shifted towards the right hand side? Which of these reactions is more forward rather than backward? Maybe we just know it. All these reactions are similar, but by the equation itself, we can't predict which reaction will shift in the forward direction more, which acid is stronger and which acid is weaker. We just cannot say by equation whether the species is a strong electrolyte or a weak electrolyte. It is absolutely purely by observation and experiment that we determine which of them will be a strong acid or a weak acid or a base. It's just known. We know HCl is a strong acid and acetic acid is a weak acid. By that, we can infer that the dissociation of HCl is favorable. The reaction shifts to the direction which has more stable species. So it can be accepted the right hand side of dissociation of HCl is more stable than acetic acid. What should be compared here? Left hand side has all neutral species. So they have the same stability as far as solution is concerned. The right hand side has charged species. Of these, hydronium ion is common. So the only species worth comparing is the conjugates of these acids. So we can infer that conjugate of HCl, that is Cl minus, is more stable than the conjugate of acetic acid, CH3COH, that is acetate ion, CH3COO minus. More stable is the conjugate, stronger would be the acid. More the reaction would be shifted to the forward direction towards the stability. Stability, by definition, is the state which the system simply does not want to change. Even if we change it, the system would revert back to the same state. These conjugates can change by accepting H plus ion. The stability for conjugates would mean they do not have a tendency to accept H plus. The species which does not have a tendency to accept H plus is a weak base. This would mean the conjugate would be a weak base. So, the final conclusion is that a strong acid has a more stable conjugate base. A more stable conjugate base has a lower tendency to accept H plus. A lower stable tendency to accept H plus would mean it is a weak base. So, a strong acid has a weak conjugate base. Weaker is the conjugate base, stronger is the acid. Same is true for bases. A strong base has a weak conjugate acid. Moving on to next concept that was given by Lewis. The Lewis concept of acid and base. A substance which either has a low energy empty orbital or has a capacity to create one, which it can use to accept an electron pair to form a covalent bond with the release of energy, is termed Lewis acid. As such, every species has empty orbital. The important word becomes the release of energy when the electrons are added to it. In the same manner, Lewis bases are the species which have a donatable electron pair. That is, an electron pair which it can use to form a covalent bond with a release of energy. These are termed Lewis bases. This donatable electron pair is either a lone pair or the electron pair forming a pi bond. Lone pair is a non-bonded electron pair in the valence shell. And understand, an electron pair means two electrons present in the same orbital with opposite spin. A Lewis acid and a Lewis base react with each other to form an adduct. Autoionization or self-ionization. In simple, day-to-day concept, a selfie, where you are the photographer and you are the subject. A reaction in which a substance forms ions by itself is termed autoionization. It may be the dissociation of a single species or two molecules of the same type, one acting as the acceptor and other behaving as donor of electrons. The examples are many, like N2O4 dissociating to give NO plus and NO3 minus. N2O5 exists as NO2 plus and NO3 minus. NH3 interacting with another molecule of NH3, ammonia with ammonia, to give ammonium ion and amide ion. And our own little simple cute water, H2O plus H2O, giving H3O plus and OH minus. One of the water molecule becomes a proton donor. Another water molecule becomes the electron pair donor and acceptor of proton. All these reactions are involving covalent species. These reactions are endothermic and not favorable or spontaneous. Water in itself ionizes to a very small extent. In this process, one water molecule becomes acid and releases H+, while another water molecule is a base and accepts H+. H3O plus is the hydronium ion. Although it is very clear that H plus does not exist, still it is an acceptable representation of hydronium ion. Using it, we can just have one water molecule undergoing dissociation or ionization. The equation now is simply a water molecule dissociating to give H plus and OH minus. There is only one species on the left hand side of the equation. In these equations, where we have only one species on the left hand side of equation, we can use the concept of degree of dissociation. We may consider that alpha moles of water dissociate per mole of water. From alpha moles of water, alpha moles of H plus and alpha moles of OH minus are formed. Multiplying the entire expression by concentration of water, taken as C, we get the final concentration of water as C1 minus alpha, of H plus and OH minus as C alpha each. Here we have an equilibrium, so we are tempted to have an equilibrium constant. Substituting the concentration in the equilibrium equation, the equilibrium constant for this equation becomes the product of the concentration of hydronium, that is the H plus, and the hydroxide, that is OH minus, divided by the concentration of water. That is, after solution, it becomes C alpha square divided by 1 minus alpha. In case of water, the experimentally observed degree of dissociation, that is alpha, is extremely small. Its elimination will not have any appreciable impact on the accuracy of result. Its inclusion only makes the calculation tedious. Hence, it is deliberately avoided and the expression 1 minus alpha is simply considered 1. You might be tempted to say that if alpha is too small, then C alpha square is even smaller. So, that also can be neglected. Here it needs to be understood that we can neglect a value only in comparison. That is, addition or subtraction, and not in multiplication or division. Alpha is very small in comparison to 1, hence can be neglected, while C alpha square is the only term in the numerator without any comparison. Eliminating this term would simply make the entire expression 0, hence cannot be neglected. So the equilibrium constant K is the concentration of water multiplied by square of degree of dissociation. Degree of dissociation in turn can be represented in terms of dissociation constant and concentration. Alpha is the square root of the product of the concentration with the dissociation constant. The initial dissociation equation tells us that the concentration of H plus, that is, the concentration of hydronium ion, is simply the concentration of water multiplied by degree of dissociation. So, simply substituting the expression of the terms, we get concentration of hydronium ion to be the square root of dissociation constant multiplied by the concentration. Water is a pure liquid. Further, it is also the solvent. Its concentration is very high and the dissociation extremely small. Its concentration remains constant throughout the reaction. There is no reason there should be two constants in the same equation. We can simply multiply the concentration of water with the dissociation constant and get a new constant. This new constant, obtained by multiplying the dissociation constant of water with its concentration, is named ionic product of water, represented as Kw. Let's now officially define ionic product of water. It is the product of the concentration of ions formed due to autoionization of water. It, of course, is an equilibrium constant. So, very obviously, its characteristics are the same as any other equilibrium constant. Just to revise, its properties are: first one, it is not affected by the individual concentration of H plus or OH minus. As per the equilibrium constants, they are not affected by the addition of product or the reactant. Similarly, the addition of acid or base would change the concentration of ions, but not the ionic product of water. Like any other equilibrium constant, it is affected by temperature. Dissociation of water is an endothermic process. In fact, it is the reverse of neutralization reaction, and an energy of 57.2 kilojoule per mole is absorbed. The increase in temperature would increase the equilibrium constant of an endothermic reaction. Hence, keeping the tradition intact, the ionic product of water, Kw, increases with temperature. The observed value of Kw at 298 Kelvin is 10 raised to power minus 14. And last but not the least, it does not depend on pressure or the presence of any other impurity in the solution. While dealing with very small or very large quantities, we have to use powers of 10. Else, the numbers would be too large with huge number of insignificant zeros. So, to do away with these zeros, we prefer to use log. Log is simply the power of 10, which gives the same number when 10 is multiplied by 10 that many times. For example, 10 multiplied by 10 0.3 times gives 2. Hence, log 2 to the base 10 is 0.3. Use of log eliminates the need to use powers and the numbers become very manageable. Further, the use of log converts the power as multiplication, and multiplication is further converted to addition. Of course, the division is converted to a quotient of subtraction. We already seen the ionic product of water is a very small quantity, 10 raised to power minus 14 at 298 Kelvin. So with that, the concentration of ions in pure water are also very low. Further, in the reaction, the concentration of these ions change exponentially with each drop of reactant. So here again, we prefer to use the log. Taking the log of the equation, we get the log of ionic product as the sum of the log of the concentration of hydronium and hydroxide ion. All these quantities are negative, and somehow we have an inherent prejudice against negative numbers. So we take an extra pain to convert these numbers to positive numbers by multiplying this entire equation by minus 1. We get minus log Kw is equal to minus log of H plus minus log of OH minus concentrations. Log of a number is actually a number which, when made the power of 10, will give back the number. All these log values in the equation are powers of concentration. By multiplying by minus 1, we have made these power of concentration positive. So the negative log of Kw is the positive power of Kw. Similarly, negative log of the concentration of hydronium ion gives the positive power of hydronium ion concentration, and the negative log of the concentration of hydroxide ion gives the positive power of hydroxide ion concentration. The symbol depicting this entire process, that is, taking the positive power, is P. Symbol P means take the negative log of whatever follows in the formula. For pH, POH, or P anything, P is short for the German word for power, potence. The abbreviation also works in French. with pouvoir as the power of. We somehow take care not to use P with the quantities which are already represented or can be represented in any case with positive power of 10. Else the very purpose of introducing the negative log will be defeated. We will end up with negative quantities. Further, in chemistry, there is an unwritten observation that if I know what I am about to tell you, you already know, then I will not tell you. Most often, the people who know a lot falsely assume that the other person also knows a lot, and under that assumption, they omit many small things which must be told. This actually is the problem that students face. Typical two sentences are, this you will do in the next class. And when you reach the next class, this you have already done in the previous class. So, here also certain things are assumed to be known. But I'll take the risk of telling them to you. In these equations, it is absolutely understood that we are talking about the concentration. Hence, the square brackets, which when placed around a quantity actually depict the concentration, are omitted. Further, this also is understood that we are considering the concentration of the ions. Hence, the charges signifying or identifying the ions also are omitted. Hence, this equation in terms of P is represented as P raised to the power K with a subscript W is equal to P raised to the power H plus P raised to the power OH. In the initial phase of printing, it was difficult to put the alphabets in the powers or as subscript. For these early days, for the ease of typography or printing, this equation simply became P small K capital W small is equal to P small H capital plus P O H capital. pH is simply the negative log of hydronium ion concentration in a solution. Similarly, POH is the negative log of hydroxide ion concentration. We know ionic product of water at 298 Kelvin is 10 raised to power minus 14. So pKW is equal to 14. With this information, pH plus POH becomes equal to 14 at 298 Kelvin. For any fixed temperature, pKW, that is the sum of pH and POH, is a constant. But the individual values of pH and POH may be different as per the system.